All right, 5.3 here, our second lesson in chapter 5. Hopefully won't be quite as intense as the last one, but it is almost the same kind of concepts, but we're flipping it around. So yesterday we talked about parallel lines and all the congruent angles, and we learned how to, if the angles are congruent, how to prove that the lines are parallel. So today is going to be the opposite. What if we already know the lines are parallel? Then how can we say that those angles are congruent? So that's what the big idea is here for 5.3. Now we do have a couple of new theorems that go along with it, right? All of our other types of angles, alternate interior, alternate exterior, corresponding, all of those things are still going to come into play, but we do have a few more. Now this first one, sometimes, it's easier to see a new theorem and kind of draw it out rather than to start with a proof and kind of try and figure out what they're trying to say. So this is really one of the big ideas on why we did that lesson back in 4.2 where we had to draw our own pictures and set up our givens and our proof statements, right? So we're going to practice doing that here to start us off. So our theorem is down at the bottom. It says, if a line is perpendicular to one of two parallel lines, then it is perpendicular to the other. And we're going to try and take that theorem, this one right down here at the bottom, we're going to try and draw the picture, write the givens, and then the conclusion based off of that theorem. Okay, so if a line is perpendicular to one of two parallel lines, so it looks like to start with, I need a pair of parallel lines, right? So here's one line, here's the other, and we could put a whole bunch of points, but let's just call these lines A and B if that's okay. And I know that these two lines are parallel, so my given would be that A is parallel to B. All right, now it says if a line is perpendicular to one of these two parallel lines, so I need a second line, right? Or excuse me, a third line. If a line, so a third line coming through, and it's going to be perpendicular to one of these lines that I already have. So if it's going to be perpendicular, then it has to look something like this, right? So this is line C, and it's going to be perpendicular to that top line. All right, so line C is perpendicular to line A. So if I have two lines that are parallel, I have a third line here coming through and it's perpendicular to one of them, then this theorem is saying that it's also perpendicular to the other. What do you think? So if I know that line C forms a right angle with this top parallel line, does it have to form a right angle with the bottom one? Well, yeah, right? If line A and B are parallel for sure, right? And C is perpendicular to the top one, that bottom line can't tilt at all. It can't have a different angle measure other than 90 because then the lines wouldn't be parallel, right? Or if the line stayed parallel and it tilted, then both of them would and the top angle wouldn't be 90, right? So the conclusion here is that line C is also perpendicular to line B. So that's kind of what this theorem is getting at. So if you already have parallel lines and you know a third line is perpendicular to one of them, has to be perpendicular to the other as well. All right, let's do that same process here on a new one. This one says, if two lines are parallel to a third line, then they are parallel to each other. If two lines are parallel to a third line, then they are parallel to each other. Okay, so on this one, let's see, what are we going to start with? If two lines are parallel to a third line, so I have two lines here, right? Here's line A, and here's line B. Okay, and each one of these are parallel to a third line, so I need a third line in here. Here's line C. Okay, two lines parallel to a third line. So I know that A is parallel to C. And I know that B is parallel to C. Right? Each one of those two original lines is parallel to the third line. Does A have to be parallel to B, right? Are our two original lines parallel to each other? And the answer is, yeah, they have to be, right? Because, so A has to be parallel to B because they can't be tilted at all or they wouldn't be parallel to line C, right? If A was going a different direction than B, then it couldn't be parallel to C. Or if A and C were parallel, B would have to be going the same direction or it wouldn't be parallel to C, right? So if you don't know that a whole bunch of lines are parallel, but you know that, like they're parallel to each other, you can kind of link them up like we do with the transitive property. All right, so those are kind of some useful things. This one is definitely going to be an interesting thing coming up as well. But next one I want you to do is another picture drawing exercise. I want you to get this set up. So draw your line and put points A and B on it. Draw point C down below. Then pause your video. Well, not quite yet. What I want you to do in a minute is I want you to pause your video and see if you can draw a line through point C that is parallel to line AB. See if you can draw in a line through point C that is parallel to line AB. Pause your video and do that right now. All right, so what I'm guessing is you guys drew in something that looked, whoops, hopefully I can draw a nice straight line. Something that looked like this. And I could almost guarantee that everyone drew the same line. And that's because there's only one possible line that goes through that other point that is parallel to a given line. And that's actually a theorem. If there is a line and a point not on it, then there is only one line. Oh, sorry. There's only one, parallel line through the given point. There we go. If there is a line and a point not on it, then there is only one parallel line through the given point. Now, this could be used in a proof, but almost never is. However, this is used when you want to draw in a parallel line, right? Just like we have the one where if we want to draw in any segment, if there are 2 points, there's a segment between them. This is if you want to draw in a certain line. If I want to draw a parallel line, that's when I would use this theorem, okay? So I'm going to make that note. Definitely do that for you as well. This is used for drawing in a parallel line, okay? So because there's only one parallel line that exists through that third point, then you can draw that line, say this is that, right? Like even if I can't draw grade, I want to draw the line that's parallel, and that's what I'm going for, okay? Now you're probably like, okay, when am I ever going to use that, right? So let me show you a situation where you would use that. So get this one all set up. This is what we call a crook problem. This is called a crook problem. Because if you take a look at the picture, notice how I have, given M is parallel to N. So I do have two parallel lines, right? If I highlight them, M is parallel to N. And then I have this transversal. But the transversal is strange because first the transversal is going this direction, and then there's this crook, and then the transversal goes the other direction. Well, that's strange, right? Our transversal never changes direction like that usually. So that's why we call this a crook problem. So you're probably like, what the heck? How on earth am I going to do this? And it all comes back to that theorem, that postulate that we just talked about. If there's a line and a point not on it, then there's only one parallel line through that given point. Do you see the point that I'm probably going to draw a line through? It's going to be going through this point right here. So if we go ahead and we draw in this line that would be parallel to M and N, and pretend like it goes through that point, right? I'm going to draw that line in see if I can actually move it here a little bit. No, that's not going to work. Okay. We're going to actually draw that line in that's parallel and goes through this point right here. And it's going to be parallel to M and N. Okay, so now I know that it's parallel to the other ones as well. And now I've broken my picture into two different sections, right? I'm still trying to figure out what is the measure of this whole angle X, right? But I'm breaking it into two different sections. So let's see. If I look at the top with my green transversal, I see a 100 degrees marked here. That's this one right here, 100 degrees. Can you see one of our special types of angles? So a lot of people first right away see alternate interior angles. So they say this one is 100 degrees as well because it's alternate interior. Some people say, ooh, I know that these are same side interior. And so that means that they are supplementary, right? That one and this guy down here. And so this would be 180 minus 100, which gives me 80 degrees. So either way you do it, right? Because you can say, okay, if I see the 100 for alternate interior, I know it's supplementary, so I could subtract from 180. Or if you see the same side interior, ooh, okay, I know they're supplementary already, so I can subtract 180 minus 100. So the top part of angle X is 80 degrees. Then I'm going to go down and look at the bottom. Here is my 40-degree angle. Now this is a separate transversal, right? My 100 does not transfer past that dotted line. That's only on the green transversal. I have a blue transversal now, so it's a separate problem. But, oh, I see alternate interior down here, right? So this one would also be 40 degrees because it's alternate interior to this guy. So angle X is really 80 degrees plus 40 degrees. The 80 degrees from my top part with the green transversal, the 40 degrees from the bottom part with my blue transversal. So X equals 120 degrees. So that's the process for a crook problem. And if you have more than one crook, more than one, the transversal is changing direction more than once. It's the same process, right? Draw in a parallel line through each one of the crooks. Wherever there is a crook, draw in a parallel line. It will break your problem apart, and then look for those special types of angles. Alternate interior is one that shows up all the time. You could use same side interior as well, right? But we're working between the parallel lines, so those are the ones that are going to show up the most. And you just kind of break it into sections and work through what's congruent, what's supplementary, and kind of piece it together until you get the parts that you need. And that's how you master a crook problem. All right, how about another situation here? So let's see. Got our quadrilateral going, and I know that AD is parallel to BC. AD is parallel to BC. And boy, I tell you, highlighting just really, really helps me. So I know that these two lines are parallel. Whoops. Okay. It says that angle D is 8x plus 20. So angle D is 8x plus 20. Angle A is 150 minus 6x. And angle C is 12x plus 60. So I have my picture all marked up. The question is AB parallel to CD? So I know that the two that I have highlighted are parallel already. I'm wondering, are the other ones parallel as well? So we're going to kind of both use what we learned today as well as what we did yesterday to kind of bring it full circle. So I know that these two lines are parallel already. So what do I know? What angles are congruent? What angles are supplementary? Okay, in order to do that, I'm going to really think about where would there be a transversal? So I have my two yellow lines are my parallel ones already. And this line DC really could be a transversal, right? Because I'm looking for alternate interior, same side interior, corresponding, things like that. So if I'm looking at angle D and angle C, these would be same side interior angles, right? same side interior. Notice they're between the two yellow parallel lines. They're on the same side of that green transversal. Some people like to say that angle A and angle C are alternate interior angles, but remember, to be any special angle, they have to both touch one single transversal. And there is not a single line that both of those angles touch, both of them touch. So there is no transversal. So those are not alternate interior angles. These, however, are both touching that green transversal of DC. So those are same side interior angles, which means that they add up to 180. And I know that for sure because I know that line AD is parallel to BC. Okay, so that means 8x plus 20 plus 12x plus 60 has to equal 180. So let's see if we can't solve for x here. So let's see. I can combine my like terms. I get 20x plus 80 equals 180. Subtract 80. I get 20x equals 100. Divide by 20. And I get x equals 5. All right, so I've got x equals 5. So now that I know x, let's see, what am I looking for? Well, let's see what our angle measures are, right? So angle A would be 150 minus 6x, and x is 5. So angle A would be 150 minus 30, so angle A is 120 degrees. Okay. Angle D is 8x plus 20. So 8 times 5 plus 20. 8 times 5 is 40. So angle D is 40 plus 20. So angle D is 60 degrees. So this one is 60 degrees. Now I already know that, angle D and angle C are supplementary. So I know that angle C would be 120 degrees, right? Because it has to be supplementary to the other one. And that was what I wrote my whole equation on, so I know that already. But now that I know 60 and 120, angle A and angle D, if these two, now if I highlight AB and DC, and then this becomes my transversal over here, that makes these guys same side interior, right? For my other line, my other parallel lines. So this time now it shows that my same side interior angles are in fact supplementary for lines A, B, and DC, right? So if same side interior angles are supplementary, then the lines are parallel. So the answer here is yes, AB is parallel to CD. For this reason, right? So our equation was set up because we knew the yellow lines were already parallel. So that equation was set up because if lines are parallel, then same side interior angles are supplementary. So that's how we got our original equation. And then since I could prove it for the other pair, that's how I knew that the other pair were parallel. So this problem was kind of an algebra problem, but it showed how you can flip around what we talked about yesterday to use it today. So if you already know the lines are parallel, then you know those special types of angles are either congruent or supplementary. Yesterday we talked about if you know those special types of angles are congruent or supplementary, then the lines are parallel. So we're just kind of doing the converse today. So to wrap it up, let's make sure that we know how to put these things into a proof. So this is going to look really similar because it looks very much like the problem we did yesterday, but it's different. We're actually going the opposite direction as yesterday. So our first step here says segment AB is congruent to segment CD. AB is congruent to CD. And step 2 says that segment AB is parallel to segment CD. So they're both congruent and parallel. But again, I'm going to go ahead and highlight in yellow because I know that they're parallel, right? And my goal is to prove that BC is congruent to AD. Oops, I'm going to put that in a different color. Proving that BC is congruent to AD. That's what I'm going to try and get to. So yesterday, we were given both pairs of congruent segments, and I was proving the segments parallel. This time I'm given the parallel segments, proving congruent. So that's the difference. All right. So if I want to prove these two segments are congruent, I'm probably going to have to prove my triangle's congruent, right? Let's see. So if I'm looking at my two triangles that I want to prove congruent, this one and this one. All right, I already have one pair of sides. Ooh, when I highlighted my two triangles, I noticed that I do have a reflexive property in there in the middle, right? So step 3, I'm going to say segment AC is congruent to segment AC with the reflexive property. I'm trying to prove BC is congruent to AD, so I don't know that yet, so I'm not going to be able to use side, side, side on this one. So if I have two pairs of sides, I probably want to try and get the angle in between them, right? So let's see, that would be this angle in my pink triangle and this angle in my blue triangle. And now I'm going to get rid of this highlight because it's kind of making me confused. Oh, wait. I already know that those lines are parallel, and here's my transversal. Yellow lines are parallel, green line is the transversal. What type of angles are those blue angles? Alternate interior, right? And since I already know the lines are parallel, then I can say that those angles are congruent. So my next step will say angle BAC is congruent to angle DCA. Be careful how you're labeling those. And that would be if lines are parallel, then alternate interior angles are congruent. Okay, so if the lines are parallel, then the alternate interior angles are congruent, right? So make sure that your if is that the lines are parallel this time. In the then part, make sure you say what type of angles they are and make sure that you say that they are congruent, right? Because no matter what type of lines you will always have alternate interior angles, but they're congruent when the lines are parallel, so be careful, okay? Now, I have my two triangles are congruent by side angle side. So step 5, triangle BAC is congruent to triangle DCA using side angle side. And again, one side was from step 1, one side was from step 3, the angle was from step 4. So 1, 3, and 4. And then once I know that my two triangles are congruent, then I can say segment BC is congruent to segment AD using CPCTC, right? Okay, so the big difference here was this time I'm given parallel lines. How do I write that reason in a proof? Yesterday, I used that the angles were congruent in order to prove that the lines were parallel. So just be careful on the order of your if and your then. And hopefully you're feeling confident now in all of those things.